Welcome to the Deep Dive, your shortcut to staying right on top of the latest in AI research. Today, we've got a really fascinating paper. It puts the world's most powerful LLMs through a pretty intense test.
Yeah, the International Olympiad on Astronomy and Astrophysics, the IOAA.
Exactly. And our mission today is basically to distill the key insights from this paper. Large language models achieve gold medal performance at the International Olympiad on Astronomy and Astrophysics, IOAA.
It's a really rigorous evaluation, I think. Probably the clearest stress test we've seen of AI moving from just knowing stuff to actually solving scientific problems.
Right. And look, we know a lot of you tune in for the quick takeaway, so let's do that first. Here's your 60-second summary of what this research really found. Because the headline's pretty clear. State-of-the-art models, we're talking Gemini 2.5 Pro and GPT-5. They scored well enough for gold medal in the IOAA theory exam.
Which is huge. That means they were consistently ranking, top 2 among hundreds of the smartest young astrophysicists globally across exams from 2022 to 2025.
But that stellar performance kind of fell apart when they switched from pure theory to data analysis.
Yeah, it really did. Only GPT-5 managed to keep up its performance there, showing much better multimodal skills. The other models, they saw these really significant drops, sometimes like 10, even 15 percentage points lower.
Okay, and here's what's really crucial, especially for engineers listening. Even with this top-tier performance in theory, these models aren't ready to be fully autonomous. There are these systematic, really persistent weaknesses.
Right. Our analysis, the paper's analysis, shows that something like 60 to 70% of the points they lost came down to failures in conceptual reasoning, geometric visualization, and basically understanding 3D space just from text.
So they can handle Einstein's equations, but struggle to visualize a basic eclipse.
Pretty much, that's the paradox.
That paradox.
Yeah.
Mastering the really complex stuff, but stumbling on spatial fundamentals, that's what makes this paper so interesting. But before we dive deeper into those failures, let's talk about the benchmark itself. Why the IOAA? Why aren't the usual tests like AstroBench or AstroQA enough anymore?
Well, it really boils down to the sheer amount of data flooding in now. Astronomy is dealing with petabytes from surveys like LSST, Gaia.
Just massive amounts.
Exactly. Humans just can't sift through it all manually anymore, so we need automated systems. But those systems have to tackle real research problems, not just simple Q&A.
And the standard benchmarks, like you said, they mostly test knowledge recall, right?
Yeah.
Multiple choice, short answers. Stuff the model might have just memorized.
Precisely. They don't force the LLM to synthesize anything new or work through a complex multi-step solution.
So the IOAA is used because it has this, what do they call it? Ecological validity.
Yeah, ecological validity. It demands creative problem solving, step-by-step derivations, multimodal analysis. You actually have to integrate knowledge from cosmology, spherical trig, stellar astrophysics, instrumentation, all to solve some novel problem. You can't just look up the answer.
Okay, got it. And the data set itself was pretty comprehensive. 49 theory problems, 8 data analysis problems covering 4 years, 2022 to 2025.
Right.
Tell us about the contamination check, though. Because that's always the big question with LLMs scoring high on tests, isn't it? Do they just see the answer somewhere?
Absolutely crucial point. So they specifically included the IOAA 2025 exam questions. These were given after the knowledge cutoff for the models, which was March 2025.
Okay. So the models couldn't have possibly seen those specific questions or solutions during training.
Exactly. And the scores on that 2025 set, they lined up really closely with the model's average scores on the previous year's exams.
So that strongly suggests they were genuinely reasoning through the problems, not just, regurgitating training data.
It validates the results, yeah. Makes the high scores much more meaningful.
Okay, so let's get into those results. Starting with the theory exams. These are the core math and physics reasoning tests. 5 top models tested: GPT-5, OpenAI o3, Gemini 2.5 Pro, and then Claude 4.1 Opus and Claude 4 Sonnet. The scores were, pretty amazing across the board here.
They really were spectacular. Gemini 2.5 Pro came out slightly on top overall, just edging out GPT-5. Average scores were up in the mid-80s% range.
Which is well above the gold medal threshold.
Way above. And just to give some human context, Gemini 2.5 Pro, GPT-5, and OpenAI o3 all scored higher than the single best human student did on the 2023 theory exam.
Wow. Okay, so we're talking truly elite human performance levels in deductive physics and math reasoning.
Definitely. They've reached that level.
But there was this really interesting kind of counterintuitive finding about GPT-5 and difficulty. It actually scored better on questions marked hard than on easy or medium ones. That seems wrong. How did the paper explain that?
Yeah, it does seem odd at first. It wasn't that GPT-5 suddenly understood hard concepts better. It seems to be more about the difference between a systemic weakness and just, well, occasional big mistakes.
Okay.
There were fewer hard questions overall, and GPT-5 just happened to nail those specific ones. But where it messed up badly, often on questions labeled easy or medium that had high point values, especially, it seems, in the 2024 exam, which had a lot of geometry.
So it's not about struggling with complexity per se, but more about these occasional, really costly slip-ups on foundational things, maybe things needing visualization or coordinate transforms.
Exactly that. It shows how just a few conceptual or geometric mistakes can really drag down the overall score, particularly if they happen early in a multi-step problem worth a lot of points.
Right, that makes sense. Okay, let's switch gears to the data analysis part. This is where things get practical, working with real data like light curves, spectra, stellar catalogs. And this is where the models really started to separate.
Yeah, this is where that multimodal capability, or lack thereof, really shines through. GPT-5 was dominant here. It actually scored higher on data analysis, 88.5%, than it did on theory.
Liar. Wow.
Yeah, which really points to its strength in interpreting plots, doing the stats, generating figures accurately.
But as soon as you look beyond GPT-5, the picture changes drastically. OpenAI O3, which was great on theory, took a big hit. And others, like Claude Sonnet 4, dropped below 50%. What does that divergence tell us?
Well, it tells us that reliably integrating text, theory, and visual data isn't a solved problem across the board yet. It's clearly an area where some players have a real edge.
So for people actually building these models.
Right, for the engineers listening, nailing the text-based scientific reasoning, that seems, well, achievable now for top models. But robustly understanding complex new scientific visualizations, that's clearly the next big challenge, the next frontier.
Okay, let's dig into why they fail. The paper broke down the theory problems into two types. Category 1, which was geometric or spatial, and Category 2, physics and math. And the performance gap was pretty stark.
It really was. It's arguably the single biggest weakness identified. Models consistently scored, 15 to 26 percentage points worse on those geometric problems compared to the physics math ones.
Even the best model?
Even the best. For geometry spatial problems, accuracy was only hovering between 49% and 78%. Compare that to the high 60s to low 90s for physics and math. It's a huge difference.
Why? Why are these spatial problems so tough for LLMs that can handle complex physics equations?
It seems to come down to how they work. LLMs operate on language tokens, right? They can manipulate the description of a 3D object or setup incredibly well, but they don't seem to have an inherent way to sort of visualize it or sketch it out mentally as they reason.
Which is what a human student would do instinctively when faced with, say, a tricky spherical trig problem.
Exactly. They draw a diagram. The LLM can't easily do that internally. So when a question needs you to really manipulate coordinate systems on a sphere, which is, fundamental in astronomy, they often stumble.
And the paper cited specific examples of these failures.
Oh, yeah. Things like writing spherical trig equations that just didn't make geometric sense, violating basic principles. Or getting confused about timekeeping, mixing up tropical and sidereal years, or treating calendar years and tropical years as the same, which they aren't. It shows a failure to model these nonlinear concepts purely from text.
I think you mentioned the eclipse problem earlier. That sounded like a really clear example.
Yes, that IOAA 2024 question, T10T, it described a non-collinear eclipse geometry. But the less capable models just defaulted to assuming the sun, moon, and earth centers were perfectly lined up.
A standard textbook simplification, maybe?
Kind of, but one that completely invalidated their solution in this specific context. They couldn't visualize the actual 3D configuration described in the text. They fell back on a simpler model instead of engaging in genuine spatial reasoning.
Okay, so if we look at all the points lost on the theory exams, what's the main culprit? Where are models losing most of their marks?
The error breakdown is really revealing. For pretty much all the models, straight-up conceptual errors were the biggest single source of lost points.
Making a fundamental physics mistake, basically.
Right. And right behind that was geometry and spatial visualization errors. Together, those two conceptual gaps and visualization failures accounted for something like 60% to 70% of all the points lost in theory.
And calculation errors.
Relatively minor in the theory section, which again suggests the bottleneck isn't math ability, it's deeper physical and spatial understanding.
That balance shifts a bit for data analysis, though, especially for the weaker models.
It does. For models like the Claude variants in OpenAI O3 and data analysis, errors in plotting, just generating the correct plot, getting labels right, that sort of thing became a major source of lost points.
But for the top performers, GPT-5 and Gemini 2.5 Pro,
for them, the main issue in data analysis was image and plot reading. And we're not just talking about failing to read text labels on a plot, it's a deeper multimodal failure in a scientific setting.
Can you give an example?
Sure. They mentioned models struggling to make accurate distance measurements using a simple scale bar on an image. They'd calculated distance, but it might be off by 20% or even 50%, just couldn't correctly interpret the visual scale. And maybe even more telling. There was an example with black body curves. Models could correctly state Wien's law and the Stefan Boltzmann law relating temperature and peak wavelength intensity. They knew the physics theory.
Right.
But when shown several graphs plotting these curves and asked to identify the one showing the correct physical relationship, they often failed.
So the abstract knowledge was there, but they couldn't connect it to the actual visual representation.
Exactly. The conceptual understanding and the visual pattern matching seemed disconnected, siloed. They couldn't integrate the two.
Okay, so let's take a step back. We've got gold medal performance in theory, but these persistent spatial and multimodal weaknesses, what does this all mean for AI in scientific research? Are we about to see fully autonomous AI scientists?
Not quite yet, it seems. The paper concludes they're definitely capable enough now to be really valuable AI co-scientists.
Like a very smart assistant.
Yeah, exactly. They can check formulas, look up concepts, maybe even speed up derivations. But their answers still need careful human checking, specifically to catch those geometric and conceptual errors before they lead you down the wrong path. They're not ready to be turned loose autonomously on research problems.
So for the technical folks listening, the paper does point towards solutions, right?
Yeah.
How do we fix these gaps, especially that big geometric reasoning problem?
Yeah, they suggest a couple of architectural directions. The main one for the geometry spatial issue is implementing something like a visual sketchpad.
A visual sketchpad.
Basically, giving the model an internal capability to visualize or even draw spatial setups while it's thinking, kind of like how humans use diagrams. They mention mimicking approaches from other research that does this.
Okay, interesting. And for the multimodal problems, the plot reading, the image interpretation?
There, the suggestion is more about data and training. Specifically, synthesizing a massive number of visual question-answering examples focused on complex scientific visuals, especially the kind you see in astronomy.
So training them specifically to connect the theory they know to the complex ways data is actually visualized in the field.
Precisely. Teaching them to bridge that gap between the math and the picture.
So the big picture here. Achieving gold medal scores is a massive validation of LLM's reasoning power in complex physics and math.
Yeah.
That's undeniable.
Absolutely. It's a major milestone.
But these really consistent failures in geometry, spatial reasoning, and multimodal interpretation, they clearly define where the hard work still needs to be done. That's the frontier for R&D right now.
That sums it up perfectly. The LLMs can grapple with and solve incredibly complex physics that would stump many humans. Yet they still often struggle to just visualize a simple 3D object moving through space. It's that gap between sophisticated calculation and fundamental imagination.
Think about that for a minute. What's the equivalent limitation in your field? The thing you work with daily. What aspect of it do you think would be hardest for an LLM, as they are now, to truly visualize or model spatially? That's maybe something to ponder as we think about where these architectures need to go next. Thanks for digging deep with us today. We'll see you next time on The Deep Dive.